Okay, Doug, working in the boiler industry, what have you found to be the most common problems with the design and installation of a deaerator system?
Okay, the deaerator in the boiler room really has a unique function. Its main purpose is just to remove oxygen from the water. When the oxygen works on the boiler, it tends to rust the boiler out. So removing the oxygen staves off the rust. Now, if you get the rusting going on in the boiler, then all of a sudden you've got maintenance costs, you've got downtime, and then eventually you're going to have to replace the whole boiler. So you've got a major capital expense there. So the purpose of the DA is basically to remove oxygen from the water. A lot of times when we do this, we can remove it down to about 7 parts per billion, and then a lot of companies will actually add a little bit of chemical scavengers that will actually remove all the oxygen from the water. But basically, if you can get the most oxygen out from the deaerator using just heat, that's a more green way to go. That's a more environmentally friendly way to go.
Tell me a little bit about what's required to remove the oxygen in the dissolved gases in the deaerator.
Okay, like we had talked a little bit ago, the deaerator is there to remove the oxygen and other non-condensable gases, basically nitrogen and some other gases that the water absorbs. Water is really an amazing substance. It'll absorb just about anything. So what we do is basically you're heating up the water. So through some various laws of physics and this, that, and the other thing, we know that if we pressurize a DA to about 5 psi, and then we also add heat to that water, it will give off oxygen. What we're trying to do with the PRV is to not only pressurize the tank, but we're trying to introduce enough heat into the system where we can bring the temperature of the water up to about 227 degrees Fahrenheit. At that temperature, that's when it starts to give off the oxygen, and we can get down to like the 7 parts per billion that we had talked about. So that's what the PRV, the pressure regulating valve, is to help us to do. Basically, you've got a valve that if you size it correctly, it will supply enough volume of steam, or what we call the load capacity of the steam, to be able to heat the water up. And then also the pressure regulator also supplies the amount of pressure into the vessel to keep it at that 5 psi. So what we need is to have the information that we can correctly size how much steam is going into the deaerator, supplying enough heat that we can get the temperature up to the 227 degrees Fahrenheit.
So what do you find to be the most tricky part about selecting the PRV?
Okay, there's a couple of things involved in that that's really kind of tricky. The first one is basically understanding how much heat you need. And then the second one is the pressure that's coming to the PRV that is supplying this heat. So the thing about supplying the heat is you need to know two things. You need to know what you're going to, or at least is the temperature that you're trying to get to, which is the 227 degrees, but you also need to know the temperature that you're starting out. So you need the delta T, or the change in temperature from what's coming into the DA to what's going out of the DA, or where you want it to be. The second part is the pressure that's coming into the DA. So what we want to get it to is whatever the boiler's supplying, we want to take it down, or we want to create a pressure drop within the pressure regulating valve that drops us down to the 5 psi. Okay, there's two things you need when you size the PRV. You need the gallons per minute or the evaporation rate of the boiler. The second thing you need is the change in temperature, or the delta T. Okay, the horsepower of the boiler, I mean, people can give you, like, I got a 600 horsepower boiler going. Okay, so 600 horsepower, you convert that to gallons per minute, which comes out to about 41 and a half gallons per minute. But actually I have two 600 horsepower boilers. Okay, so two 600 horsepower boilers converted over to gallons per minute is about 83 gallons per minute. Okay, so that's the evaporation rate. That's one of the things we need to know. The second thing we need to know is basically what the change in temperature is, or the delta T. Okay, so when you get the delta T, basically what you got going into the deaerator is you have fresh water coming into it. That's what we call the makeup water. And then you have the condensate returns going into it. Okay, so from these two things, we get what we call the mixed temperature. Okay, so if I have, say, I have no condensate return coming back.
Right.
I just have fresh water makeup coming in at 60 degrees. Okay, so theoretically my mixed temperature is 60 degrees. Okay, now if I have 100% condensate coming back at 180 degrees and no fresh water, then my mixed temperature is 180 degrees. Okay, so it sounds pretty easy. But then if I have 50% condensate coming back at 180 degrees and 50% makeup coming in at 60 degrees, all of a sudden my mixed temperature is 120 degrees. Okay, so I take that and then I subtract that from the 227 degrees that I want to get to. So if it's just 60 degrees, I've got, what is that, about 147 degrees?
Correct.
I've got to make up in temperature. But if I've got all condensate return coming back, then all I have is like 47 degrees to make up in temperature. So that's quite a range between 167 degrees and the 47 degrees. Okay, that's why we need to know the condensate return, is because then we can, by knowing how much we have to raise the temperature, then we can figure out how much steam we actually need. Okay, so from the steam that we actually need, for the gallons per minute that the boiler is asking for, then we can size the valve.
If you have two 600 horsepower boilers with a total load of 1,200 horsepower, how important is that versus the actual operating load?
Okay, that's where we get into trouble with a lot of companies. They'll call in and they'll just say, well, we just figured the worst case scenario. Okay, so we had this one company that called in. They wanted 3 600 horsepower boilers, and they wanted a redundant boiler or a backup boiler. Okay, so we went through the numbers. They were real good at giving us the condensate returns, the temperatures, the makeups, all that stuff. They were really good at that. So we went through and we figured it for the 3 horsepower or the 3 600 horsepower boilers going at full load. Okay, so after they got it installed, it wasn't very long before they started having trouble with the pressure regulating valve. It started chattering on them, which basically is a sign that the valve is too big. Okay, so they called us up, hey, we're having trouble. So we went through the numbers again, and all the numbers are coming out the same. We had sized the valve correctly according to what they gave us. Now, they were still having trouble, so Watson McDaniel sent a rep down there to kind of investigate this for us.
Right.
And what they said, or what he found out, and the information they gave him, he also came to the conclusion that we were too large. Okay, so based on what they told him versus based on what they told us. So after going through the numbers for a third time, we finally sat down, okay, well, how many boilers are you running?
Okay.
So they asked for 3 600 horsepower boilers, but at the time they were only running 1. And when they came back, they said, well, we're running 1 boiler between 75% and 100%. Now, when it gets colder out, we're going to be running 2 boilers. Okay, and then when we finally get the whole campus up to grade, we'll have 3 boilers running full speed. So the whole thing, they gave us good information right off the bat for a completed deal.
Right.
But we didn't get the good information for the stages that they were going to build this thing in. Okay, so we started off with 1 boiler, then it's going to go to 2 boilers in cold weather, and then when they finally get it all done, it'll be 3 boilers. Now, the difference between running 1 boiler at 75% and running 3 boilers full out is quite a difference. So
what happens when that range is too large?
Okay, so what happens is if the range is too large, you have a really large valve. Okay, so the valve is going to sit there and try to open, but because the valve is so large, it lets enough steam through at just a small amount of opening. So the valve will sit there and just kind of bounce back and forth, opening and closing. You know, it opens and all of a sudden it sees the pressure, then it closes, you know, and it
So
just
it just
continues.
chatters.
Yeah, it chatters. That's what it does. And when it does that enough, you'll eventually destroy the valve. Okay, so that's what happened in this case. The valve came back, and that's what we sent it back to Watts McDaniel. They inspected it, and that's basically what it was the valve was too large for what they were operating at that time. Okay, so working with Watts and McDaniels, we came up with a system that basically, say, a 1/3, 2/3 system. We had one valve that was big enough to handle one boiler. Then we had a second valve on there that as soon as the second boiler kicked in, then the second valve would start to open up. So neither valve was too large for the thing, but both of them together will manage 3 boilers at the end.
So having it split 1/3, 2/3 gives you the turndown required based on the load.
Yes. Yeah, that's exactly what we did.
Doug, earlier you mentioned that the pressure is also a consideration when sizing a PRV. Can you tell us how so?
Yeah, the pressure is kind of a tricky thing because what you got, and basically you know this, that the lower the pressure, the bigger the valve has to be because you're trying to move a lot of steam. Okay, so the valve has to be bigger. Now, if you got a higher pressure, the valve can be a little bit smaller because you're pushing it faster, so you can get more steam through the valve.
Okay.
Okay. The deal with the pressures, though, that we found in some installations is that, say I need 110 PSI, I'm getting 110 PSI operating from the boiler that's supplying the steam.
Correct.
Okay, so this boiler is setting way off somewhere else in the factory, somewhere else in the plant. And through the piping that's going on, you get a lot of pressure drops. So what's actually happening is as this 110 PSI is coming to the DA, it's losing pressure through the pressure drops, the piping, and all that. I ran a quick scenario on that just to see what would happen. And let's just say at 110 operating pressure, we lost 15 PSI through the pressure drops of the piping system that they installed because the boiler is so far away.
Okay.
Okay. Let's just say 2-inch full port valve was the correct sizing at 110 PSI. Okay. When I ran the numbers through the program that Watts and McDaniel supplied us with, it ended up dropping. Well, if you drop at 15 PSI, you basically go from a 2-inch full port valve to a 3-inch full port valve. So just even the small amount of 15 PSI can affect how the valve's going to operate and how much steam you get into the DA.
So we need to take into consideration the piping losses prior to the PRV before it enters into the deaerator.
Yes, we do. And a lot of times we just kind of assume that it's negligible. So we don't really pay a lot unless we know that the boiler's going to be pretty far off. Then we'll start pushing to get more information of how big the pressure drops are going to be and where they're coming from.
What would make it easier for us to size if we had a full set of drawings, we had an idea? Is there something to consider?
Basically, a lot of times our reps do a really good job of getting out there and digging out this information for us.
Right.
And that's kind of what we need is for them to get in there, find out what the system's going to be, find out where the locations are. And yes, a lot of times drawings will do that for us, but sometimes the drawings don't quite speak to us like a rep would.
Correct.
So our reps do a good job of that, but sometimes we don't identify that soon enough. So that's one thing we need to be on top of is just exactly what's going on in the plant.
Doug, let's say you've been given all the information to properly size the PRV for the application. Are there any other pitfalls that could happen?
Okay, once you get through the design phase, then you're entering into the installation phase. Okay, there's quite a few pitfalls that we come across there. The first thing about the PRV is it has what they call a pilot or a pressure pilot on it. That's the one we predominantly use. The pressure pilot has a sensing line that goes down the line. You tap into the pipe, and then the pressure, the PRV actually reads the pressure downstream of it. That way it knows how to adjust itself. Okay, what they want in this situation is they want the flow of steam to be more laminar. Okay, so they recommend putting the tap for the pressure sensing line about 10 pipe diameters downstream of a straight run. This way the steam has a chance to settle back down. It gives a nice, gentle, stable pressure at that point. And then the PRV is not trying to read something in a turbulent area. Okay,
So the pilot line is sensing the downstream pressure, which it's trying to maintain, say, 5 psi blanket on the deaerator.
Exactly. Okay. So that's what we're shooting for, is a nice laminar flow that the pressure can, the PRV can read, and then it sets itself, and so that's what you get. Okay, the problems that we've seen in the past is one time we went into an installation and they didn't even plumb in the pilot valve, or the pressure pilot.
So it had no way to sense the downstream pressure?
Yeah, it had no way.
So how would it be adjusted at that point?
Well, and I think this is what happened. There are different regulator valves that you can adjust and then just leave alone. They don't need a pressure sensing line.
Okay.
That was not the case for this one. So they just plumbed in the PRV, left the pressure sensing line out, and then went to town. And it didn't work. So in that case, it was a pretty easy fix because you can always tap into a line downstream a ways. But recognizing the fact that they needed that was part of the problem. They didn't have it. And so going in, we could see that they didn't have it. So we made the recommendation and it was fixed, and then everything worked out fine. The other problem we've been seeing is like with a multiple orifice plate. These are designed to slow the velocity of the steam, and when they slow the velocity of the steam, it actually decreases the noise that the steam is creating as it flows through the pipes. Okay, it also is part of the design of the PRV. So when we're designing the PRV, we take the multiple orifice plate and the pressure drop that goes across it, and we add that into the PRV. So the PRV by itself will not get to the pressure drop we need. The multiple orifice plate by itself will also not get to where we need to be. So they need to be installed together as close as possible. A lot of times, basically coming right out of the PRV will increase the pipe size large enough to be able to mount the multiple orifice plate. So you want this mounted as close to the PRV as possible. And sometimes you'll just go to the downstream side of a shutoff valve. The shutoff valve is usually found like in a 3-valve bypass. Okay, one of the things, well, there was one time I went to an installation and I got to looking around, and they had all the PRV was mounted, everything was up in the ceiling, so it was about 20 foot over your head.
Oh, great.
Okay, so I got to looking around. Then I was kind of looking around the deaerator. Down underneath, I found the multiple orifice plate laying in some of the packing that it came with. So they not only didn't put it in, it wasn't even considered to be put in. So there's no way that was going to run the way it was designed to run. Okay. Another instance we went into, and they basically laid the multiple orifice plate on top of the steam inlet valve, or on top of the steam inlet on the deaerator. So there's no way it could really work as far as being a noise suppression plate, because it's already downstream of where all the noise is going on. Okay. So that was not a good spot either. So like I said, the two things we've seen is the pilot, installing the pilot correctly, and also considering the multiple orifice plate and how to install that is the two things with the installation we've seen.
So the multiple orifice plate does two things. Slows down the velocity, which reduces the noise, basically conditions the steam before it goes into the deaerator.
Yes. Okay. Yeah, that's exactly what it does.
And it's integral to the PRV in some circumstances.
Yeah, when you size the multiple orifice plate, the PRV is depending on the pressure drop across that multiple orifice plate to get to where it needs to be. Because the pilot line will tap into the line downstream of the multiple orifice plate.
Okay.
So the pilot line does read the drop across the multiple orifice plate.
Now that we have the PRV selected and sized and installed, what other pitfalls could you see on the operation side?
Okay, once you get through the installation phase, you get everything in and operating, then it's just a matter of operating the DA. A lot of times, well, what you want to do is you want to keep the DA at 227 degrees Fahrenheit because that's the optimum temperature where water starts to give off the oxygen.
Right.
Okay. You don't really care about pressure at this point. You do, but you don't. So an operator needs to keep an eye on the temperature. One installation I went to, they were reading 5 psi on the panel mount pressure gauge, but the deaerator was wide open. I mean, it was down for maintenance. The doors were open on it. There was no pressure in the vessel other than atmospheric pressure. What had happened was when they plumbed the panel mount pressure gauge in, they used 1/4-inch tubing, and the tap in is like way up on top. It was like 20 foot in the air. Okay, so then it drops down to the panel mount, which was basically eye level.
Right.
So what they failed to do was put in a drip leg in there. So when the water, or when the steam got into that pressure line, it condensed into water. So now you had all this water sitting on top of the pressure gauge.
Correct.
So it read 5 psi no matter what happened. Okay?
So they had artificial information.
They did.
Misinformation.
Basically, they needed to plumb in a drip leg. That way they could let the water off of that line. Then they could get accurate information on the pressure gauge.
Right.
Okay, that's why you really need to just keep an eye on the temperature. When the temperature starts to get up there to the 227 degrees, if you're running 5 to 12 to 15 psi, it's not an issue because the deaerator's been designed up to 50.
Okay.
So basically, in an operation mode, you really need to keep an eye on the temperature versus the pressure.
So the amount of makeup or the flow at which the deaerator is running, it can have a cause and effect on the steam blanket, which is the pressure. So the pressure is not the most important item, it's the temperature within that. It may take more pressure to maintain the 227 depending on how the deaerator is operating.
Yeah, roughly, because theoretically it's 5 psi for 227, but we know when you get out in the field, it's not always theoretical. You know, it's actual. And that's where you got to kind of, like you were saying, we need to keep an eye on the temperature. So what you're looking at on the pressure gauge may or may not be exactly the pressure inside the vessel. Like in the situation I was talking about, you had this buildup of water in the tube that basically gave you a false reading.
Okay.
So you need to be aware of those kind of issues also.
Right. So the real key here is to make sure you're maintaining the 227 degrees.
Yes, that's the key. That's where your bread and butter is.
Perfect. Doug, earlier you mentioned the two main components for the deaerator are the pressure and the water. Can you tell us a little about some of the problems with the water inlet valve?
Okay, when you size the water inlet valve, basically you're looking at the condensates also. The water inlet valve is sized specifically for the makeup water. Okay, the condensates are going into the DA by itself. They don't flow through the water makeup valve. So if you've got 50% condensate coming back, well, let's just say you've got 100 gallons per minute. The DA needs 100 gallons per minute to keep up with the boilers.
Okay.
Okay, if 50 gallons per minute, that's coming back in condensate, all you need the water inlet valve to be sized for is 50 gallons per minute. Okay, so whatever your makeup water is going into the DA, that's what the valve needs to be sized for. Now, on the other hand, if you have a surge tank that's actually feeding the deaerator, and as you know, the surge tank collects all the condensates, all the makeup water, everything is pumped into the surge tank. So via the transfer pumps, that's what sends it to the DA. So the water inlet valve needs to be sized to the point where it can handle all the flow of the transfer pumps going into the DA. Okay, because 100% of the makeup, well, I should say in this instance, 100% of the makeup going to the DA is coming out of the surge tank.
Okay.
Okay, so the valve needs to be sized for that.
Sounds like the condensate has a cause and effect on both the PRV and the feedwater valve.
Yeah, the condensate's really important. If we can nail down the condensate, that's a good thing. You know, because a lot of times they'll come back, the companies that we're building these things for, they'll come back and say, well, just use 100%, worst case scenario, use 100% makeup water.
Right, at default.
Yeah. Yeah, that's
It's a safety
easy.
factor, right? 100%.
Yeah, that's the way they take it, is it's a safety factor. You know, just 100%, worst case scenario. But unfortunately, what we've seen is sometimes when you do the 100% worst case scenario, you are getting the worst case
Scenario.
of operating. Okay, so yes, you need to really understand your condensates, you need to understand the makeup, you need to understand the pressures. And like I said, our reps do a good job on supplying this information, and that's the information we need.
Now that we've touched on the PRV and the feedwater valve, are there any other piping concerns between the PRV, the feedwater valve, and the deaerator?
Now that you mention it, yes, there is. One of the concerns we have is when the pressure comes out of the PRV, or when the steam comes out of the PRV, the pipe size is considerably bigger. Like you might have a 2-inch line feeding the PRV, and then coming out of that, you have a 8-inch line in the deaerator, okay? As soon as you get out of the PRV, you need to increase the pipe size to that 8 inches, and that needs to travel all the way to the deaerator.
Okay.
Sometimes people will come out of the PRV, they'll go across the multiple orifice plate, and then they'll drop the line back down to 2-inch, thinking, well, I got 2-inch coming in here, I got 2-inch going out there. Once it comes out of the pressure regulating valve, it needs to increase, because what you're doing is you're slowing the flow of steam down. And when you slow the flow of steam down, so that way when it gets into the deaerator, it's not blasting into it, you know, it's not hitting it at full force or the 110 psi. You want it to go in at a steady pressure, but it needs to be a little bit slower, and that's why the line after the PRV is sized considerably larger than what's going into the PRV.
Okay.
Too many times we've had people that will actually try to save some money and drop it back down. We don't want to do that. We want to keep it at the size that is coming out of the PRV. And there is a predetermined size for that. So if there's questions on that, please feel free to get a hold of us, and we can walk through that with you also.
Now that we've completed our conversation regarding PRVs, feedwater valves, installation pitfalls, piping pitfalls, and common issues, we'd like to open it up to a few minutes of questions and answers. If you have a detailed question, we can try to address it now, or you can schedule an appointment with one of our engineers.